My goal in this video is to highlight the idea of optimal substructure in dynamic programming problems, including how it relates to both top-down and bottom-up algorithms, as well as how it generalizes when we have more than one dimension of subproblem. We'll primarily do this in the context of an RNA folding problem, but first I'd like to think back to our two previous problems of weighted interval scheduling and word separation. We approached these two problems from opposite directions, designing a bottom-up dynamic programming algorithm for weighted interval scheduling and a top-down memoization algorithm for word separation. But in both cases, we ended up filling in a table with optimal solutions for different subproblems, and could also add an auxiliary table to keep track of the choices we made along the way and reconstruct the sequence of decisions that led to the optimal value. And so, in both of these cases, the optimal value and the optimal choice on any given problem can be defined in terms of previously found optimal values for subproblems. For example, in weighted interval scheduling, we can think of the optimal value for up through the ith job as a function of the optimal up through I-1 and the optimal up through job j, the one that finished before I starts. And so we can write down a formula for the ith entry in our array of optimal values in terms of previous entries in the same array. Likewise, for word separation, the optimal word count when we started at index b was a function of the optimal word counts we found at the various later indices that were right after some word beginning at B. And so again, we can write out a formula for entry B in our array of optimal word counts. Here, our equation is a little more complicated because S ranges over the rest of the story for any of the places where we could get a word before the split. But it remains the case that if we have the optimal values for smaller subproblems, then we can straightforwardly write down the optimal value for a larger problem. And so, in a sense, these equations for the entries in the optimal value array completely define the dynamic programming algorithm. Given either of these equations, we could write a bottom-up dynamic programming algorithm where we compute opt of 1 and opt of 2 and so on, or a top-down memoization algorithm where we compute opt of n recursively in terms of smaller subproblems. And in addition to getting us most of the way towards a dynamic programming algorithm, these equations also give us a big head start on a proof of correctness, because the inductive step of our proof will follow exactly this same sort of reasoning. So when we see a new problem that we think we can solve with dynamic programming, our goal should be to try and identify this sort of optimal substructure. Specifically, how does the optimal solution for a larger problem depend on the optimal solution to smaller problems? And if we can write down an equation for that relationship, then we are a big part of the way towards writing our algorithm and proving it correct. With this in mind, let's try and identify optimal substructure in a new problem where we're trying to predict how a molecule of RNA is likely to fold onto itself. The motivation behind this problem is that when biologists read the content of an RNA molecule, they see a sequence of A, C, G, and U bases. And that can say a lot about what that RNA is encoding, but it doesn't say how that molecule of RNA will behave in various chemical interactions. To understand the behavior of the RNA, it helps to also know the shapes that it will fold into, because unlike DNA, RNA is single-stranded, which means that it doesn't have a nice double helix shape, and so instead of having a second strand that it pairs with, a molecule of RNA is likely to fold up and match with itself. So in our version of this problem, we are given an RNA sequence, which we can represent as just a string of characters representing the bases. And our goal is to figure out how the strand of RNA represented by that string will match up with itself. What we will output is a matching represent where bases have paired up. So to represent this structure, we would output the pairs 2, 11, 3, 10, and 4, 9, indicating the indices along the strand at which pairing occurred. And so our goal is to match up as many bases as we can, subject to some constraints that describe the way in which RNA typically folds. The first constraint is that A bases match with U's and G's match with C's. Second is that this is a matching where we only have one pair for any given index. Third is that these sorts of hairpin structures cannot turn too sharply. Because the backbone of the RNA molecule has physical constraints, it cannot directly turn around from a U to an A. There has to be some number of unpaired bases for it to loop around like this. That gets encoded in our algorithm as a constraint that we can only match to indices if there are at least 4 elements in between. So this example that I've pictured is the tightest bend that we are allowed to have in a hairpin. And our last constraint is that we don't have crossing pairs, which we can represent mathematically as for 4 indices in increasing order, we don't have I and K paired, while we also have J and L paired. So if we are given this RNA string as our input, then our optimal output, the most matches we could make subject to these constraints, is in fact representing this structure by the pairs 2, 11, 3, 10, and 4, 9. But it's also worth thinking about what sorts of things are ruled out by our constraints. And so example 2 shows lots of ways that the matching could go wrong if we violate one or more of the constraints. The first problem here is that we have I, J, K, and L, 1, 2, 14, and 15, that are in ascending order, but we have I and K matched and J and L matched, which corresponds to the red lines for the matching having to cross. The next problem here is a violation of the matches being 1-to-1, which is that we have 3 matched with both 12 and 11. We also have a violation of constraint 3, that 2 things we match must be at least 5 apart, because we have matched 6 and 8, and those have a distance of only 2. And finally, we have a violation of the first constraint, because when we matched 4 and 10, those are both G, which is not a way that the RNA is likely to fold itself. So now that we understand the RNA folding problem, we'd like to write a dynamic programming algorithm to solve it. And that means we want to try and identify the optimal substructure within this problem. Since our goal is to maximize the number of bases we can pair, the optimal values that we will keep track of will be a number of pairs, and our eventual goal is to find the optimal number of pairs that meet the constraints in the entire length n string. But we can think of subproblems where we solve the maximum number of pairs up through some endpoint e. So let's try to define the optimal number of pairs up through some endpoint e in terms of smaller subproblems. Well, our smaller subproblems would be the number of pairs from 1 up to some midpoint between 1 and e. And if we have previously solved the smaller subproblems, then the optimal that we can achieve up through e could either happen by pairing e with some previous base, or by not including e in a pair and having it be one of these that dangle off the end. In the case where e is unpaired, then the optimal value at e would be the same as the optimal value at e minus 1. So one of the possibilities we should consider is that the best we can do is just to take the number of pairs up through the previous base, and if that's larger than any of the other options we consider, that will still be optimal at e. On the other hand, if we pair e with some previous base m, we know that m has to be less than e minus 4 in order to satisfy constraint number 3. And so we can take the best value from the different subproblems corresponding to matching e with a base at index m, where m can be anywhere from 1 up through e minus 5. So if we match up e with m, then that will give us one pairing, plus however many additional pairings we can make after we have done this pair. And so there could be some other pairings that happen in this range, and there could be some other pairings that happen in this range, but because of the no crossing constraint, number 4, we know that if we are pairing up these, there cannot be any element before m that gets paired with any base between m and e. It's still possible that there could be pairings within this range or within this range, but those are subproblems. And it's also possible that there could be pairings from this range to this range, but we'll handle those when we get to larger instances. Because right now we are only trying to find the optimal number of pairings up through element e. So, because there cannot be any pairings between these two subregions, that means those are totally separate subproblems. And those are smaller subproblems, so hopefully we can find those values already in our opt array. The left subproblem goes from 1 up to m minus 1, and so that is one of the smaller subproblems that we would have already encountered. But we also have to add in the optimal number of pairs within this range, and we don't yet have any subproblems in our array corresponding to a starting point of m plus 1. And so here we recognize that we need two different dimensions to our table of subproblems. In our previous dynamic programming problems, we either had subproblems that always started at the beginning, or that always finished at the end. And so we could represent any subproblem by either just its end index or just its start index. But now we have subproblems where we need to represent them by both their start and their end index, which means we need a two-dimensional table. So now our table of subproblem optimal solutions will have two indices for the start and end of the subproblem. And so the left subproblem that we were including in our equation is the subproblem from 1 up through m-1. And now we can talk about this subproblem as an entry in the table, specifically the one with start index m+1 and end index e-1. And we'll also need to change our indexing of the one smaller problem, where if we're talking about the optimal value from start to end, in the case where we don't pair element E, that optimal value would just be equal to the optimal from start up to n-1. And now we have a full equation for the optimal value of a subproblem starting at S, ending at E, in terms of smaller subproblems, either from S up to E-1 or from 1 to m-1 and m+1 to e-1. Since all three of these are smaller subproblems, as long as we solve our subproblems in increasing order of size, then we will always be able to calculate the optimal value from a given start to end point in terms of previously calculated optimal values. Of course, all of this was assuming that M was a base that could be paired with E, and so as we did before, we should write down the restrictions on this variable M. It not only has to be between the start and E-5, but it also has to be a base that can match with E. So this equation tells us how we could implement a bottom-up dynamic programming algorithm or a top-down recursive algorithm with memoization, and gives us a big head start on proving those algorithms correct. But since we've seen these one-dimensional algorithms in action and how the dynamic programming tables get filled out, let's do the same for RNA folding. And to reinforce the point that this equation captures virtually everything we need to know about the algorithm, let's fill in the tables without even writing down pseudocode for the algorithm. As usual, we'll have one table to store the optimal values and a second table to store the choices that led to the optimal value, which will let us reconstruct the actual pairing at the end. And both of these tables will be a two-dimensional array where the row number tells us the start index and the column number tells us the end index. Let's try and come up with an actual solution for example 2. So we'll use this example for our tables. So the characters of the RNA string will correspond to the rows and columns of this table, where the start index specifies a row and the end index specifies a column. But because of our constraint that we cannot pair anything that are within a distance 4 of one another, that means we actually don't need the first 5 end indices or the last 5 start indices. In addition, because the start index comes before the end index, we don't need anything in the bottom left portion of this table. So let's redraw the portion of the table that we actually need. Because the optimal solution for a subproblem depends on smaller subproblems, it makes sense to order our filling in of the tables from smallest subproblem to largest. The smallest subproblems are the ones where we have a distance of just 5 from the start index to the end index, and those appear along the diagonal of the tables. Then, as we work our way up to larger subproblems, we will move up further diagonals of the table until we eventually reach the top right corner with the subproblem that goes from index 1 to 15, which will tell us the optimal number of pairs for the entire example string. Along the way, it will be helpful to keep track of what start and end index we're on. And based on the end index, that will tell us what we need to pair it with. If the character at index E is an A, then we should only consider M if that character is a U, and so on. And in figuring out the optimal value for a given subproblem, we'll need to consider the previous subproblem for n-1, and we'll need to consider the sum of 1 plus the optimal values in these two subproblems, which we'll put in this column. So beginning with our first subproblem, we have a start index of 1 and an end index of 6. At index 6, we have an A, and so we need a U to pair that with. The previous best we could do was 0, because on smaller subproblems we can't make any valid pairs. And here, the only value of M that we can consider that is at least 5 away from E is 1. And since index 1 doesn't have the character that we need, this gives us a value of 0. And so the maximum number of pairs we can make in this subproblem is 0. And in our choices array, we would record the M that was best if there was one, but since we didn't find a valid split or an optimal split, we just record a 0. Our next subproblem is from 2 to 7. Index 7 has a G, so we need a C, and index 2 is not a C, so again we are going to get 0. For the subproblem from 3 to 8, we have a U and need an A, and that is in fact the character at index 3, so our previous is still 0. The only valid value of M here is 3, but for that instance, since A matches U, we get 1 plus the optimal. This should be from start. From the start up to m-1, and since our start was 3 and m-1 is 2, this contains no pairs. And we look at the optimal from 4 to 7, And since 4 to 7 is too close for any pairs, that's also 0. And so we get a total of 1 here, which is better than our previous of 0. So we fill it into our opt array. And in our choices array, we record the thing that we paired E with to get that optimal value, which was our M index of 3. Our next subproblem from 4 to 9 also has a match between G and C, and so we're again going to get 1 plus 0 plus 0 for an optimal value of 1, and we will record the M index, which in this case was 4. Our next pair from 5 to 10 has a G and a G, so that doesn't match, and we get an optimal value of 0. From 6 to 11, we have an A and a U, which do match, so again we're going to get an optimal value of 1, and we'll record our M value of 6. And the rest of the way, we don't have any more matches. We have G against U, U against C, C against A, and G against U. So all of these will have no valid pairs. And we fill in zeros for both tables. Now that we've completed all of the size 1 subproblems, we can move on to the size 2 subproblems. And the first one we encounter is from index 1 to index 7. Index 7 has a G, so we need a C. The previous subproblem is from the same starting point up to end minus 1, so that's one cell to the left in our opt table, and here we get a value of 0. And now we have two different values of M that we could consider. We could have an M of 1 or 2. When M is 1, we're trying to match G with G. That doesn't work, so we get an optimal value of 0. And when M is 2, we have an A and a G, which again don't match. So the maximum value for any M is 0, and the previous value was 0, so we fill in a 0 for the optimal value, and a 0 in the choices table, indicating that we didn't find a good split. Our next subproblem is from 2 to 8. We have a U, so we're looking for an A. And here, M could be either 2 or 3, and both of those indices have an A, so it looks like we're going to find a match here. Our previous value, again, is immediately to the left in the table. And with an M of either 2 or 3, we end up getting 1 plus a too small problem to the left and a too small problem to the right, so we get an optimal value of 1. And we'll suppose that the max picks the first thing with the optimal value, meaning that we will fill in a value of 1 in our opt table and an M index of 2 in our choices table. This assumption that we will take whatever is the first index that gives us the maximum value will allow us to cut some future searches short. So if I have found the best, I will stop searching through subsequent indices. In particular, when we get to our subproblem from 3 to 9, our previous value is 1, and since from 3 to 9 we only have 6 bases, what's left when we take out those 2 is just 4 bases, which are not far enough apart to have any additional matches, and so just based on the size of the problem and the previous being 1, I immediately know that the opt will be 1 here, and I can fill in a 0 in the choices table saying, just go back to the previous problem where we found a pairing between 8 and 3. Likewise, for 4 and 10, the previous problem is still going to be optimal. And now we get to the 5-11 subproblem. Index 11 has a U, so we're looking for an A. Our previous best was 0, And the valid indices for m are 5 and 6. Since 5 does not have an A, we'll skip it, but since 6 does have an A, we will get one match plus two subproblems that are too small to have any matches, so we'll get an optimal value of 1, and we'll record the m index of 6 that got us that value. For our next subproblem from 6 to 12, we again need an A, but for the same reason as before, the previous is already 1, and we're not going to do better than 1 with our current subproblem size, so we can just fill that in with a choice of 0, saying go back to the previous subproblem to find the pairing. From 7 to 13, we have a C in the end index, so we need a G. Our previous entry in the opt table is 0, and one of the two possible m's, 7 and 8, has the letter we're looking for, so in that case we'll get 1 plus 0 for an opt of 1, and we'll record that 7 was the m index that got us there. For 8 through 14, we're looking for a U, and we have it at index 8, so we'll get a 1 and m equals 8. For the 9 to 15 subproblem, we're looking for an A to match with this U, and we don't have it, so we end up with whatever was the previous best, which was 0, and we fill in zeros for both tables. Moving on to the third smallest subproblems, we next look at 1 through 8, and these problems are now large enough that it's possible to have two pairs, for example 1, 8, 2, 7, before we get within distance 4. Our first subproblem is 1, 8. Index 8 has a U, so we need an A. Our optimal value for the previous subproblem was 0, and our m values for this subproblem are 1, 2, or 3. Since both indices 2 and 3 have an A, both of those will give us a value of 1 plus the optimal solution from 1 up to 1 or 2, which is 0, plus the optimal solution from 2 or 3 up to 7. So that does include a valid subproblem, which is from 2 to 7. So we can look up in our table the 2 to 7 subproblem, and that had an optimal value of 0. So in either case, we get 1 plus 0 for an optimal value of 1. And we'll just record the first one that gave us that optimal value, which is an m index of 2. Next, on the 2 to 9 subproblem, we have a C and we're looking for a G, and our previous value is now 1 from the 2 to 8 subproblem. M ranges over 2, 3, and 4, and at index 4 we have the character G, so we need to consider whether that subproblem does better than our previous value of 1. When m is 4, the subproblems go from 2 to 3, which is too small, and from 5 to 8, which is too small. So even though this is a match, it's no better than our previous, and we can just fill in the previous value carried over, and 0 indicating that we can just go back to the previous for our best match. On 3 to 10, we're looking for a C, and we have a previous value of 1. The indices we're looking in here are 3, 4, 5. Since none of those are a C, we're going to get zeros here, and our best will come from the previous. So we get a value of 1 and a choice of 0. From 4 to 11, we're looking for an A, and this is in indices 4, 5, and 6. We find an A in index 6, but that leaves us with subproblems of 4 to 5 and 7 through 10, both of which are too small, so the best we can do is 1, which is equal to our previous value. So we'll take the one that came first, filling in a 1 and a 0 indicating that we got there from the previous. For 5 and 12, we again have a previous value of 1. We're looking for an A in indices 5, 6, and 7. 6 has an A, but the subproblems will be too small, so the best we can do is still the previous. Again at index 6, we're looking for a G, and we find one at one of our valid M indices, but the subproblems will be small enough that we end up with another tie at 1, and so we'll just keep the previous. From 7 to 14, we're looking for a U among indices 7, 8, 9. We find a U in index 8, but only index 7 would have given us a large enough subproblem for more pairs, so again we tie with the previous. And from 8 to 15, we're looking for an A and don't find it, so we just keep our previous value of 1. Now moving on to the size 4 subproblems, we start with 1 through 9. There will now be 4 values of M each time, and so we're looking for a G in indices 1 through 4. We find one in index 1, so we get 1 plus the optimal before index 1, which is 0, plus the optimal from 2 up through 8, which is one of our subproblems. And when we look in our opt table, we know that that subproblem already has a value of 1, and so now we have a way of making 2 pairings. This is the best we can do, so we'll skip the remainder, and our optimal value is 2, and the index that got us that is m equals 1. So what this is saying is that we can get 2 pairs by pairing 9 with 1. The implied subproblem is 2 through 8, so we can go look up that subproblem, and we'll pair 8 with 2. So 1 to 9 and 8 to 2 gives us G to C and A to U, so we do have 2 valid pairs in the 1 through 9 substring. On the 2 through 10 subproblem, we're looking for a C in indices 2, 3, 4, 5. We don't find one, so we just take our previous value, which is 1. On 3 through 11, we are looking for an A, and we have one at either index 3 or index 6. Our previous value was 1, so the question is whether we can beat that. When we pair 11 with 3, then the subproblems are too small for the left side, and 4 through 10 for the right side. We can look up the 4 through 10 subproblem, and that is one where we got a value of 1, so we'll get 1 plus 0 plus 1 for an optimal value of 2, which we can't beat on this subproblem size, so we'll quit looking and fill in an index of 3. On 4 through 12, we're looking for an A to pair with the U. We have a previous value of 1, so we find an A in index 6, but that leaves us with subproblems of 4 to 5 and 7 through 11. Both of those are too small to find any additional pairs, so this is no better than our previous value of 1. On 5 through 13, we have a previous value of 1. We're looking for a G to pair with the C. We look in indices 5, 6, 7, and 8 and find G's at 5 and 7. At index 5, our right-hand subproblem is 6 through 12, which we can look up, find that that contains a pair, so we get 2 pairs and an optimal index of 5 in our choices array. From 6 to 14, we're looking for a U, find it at index 8, but at that point our subproblem 9 to 13 is too small, and we end up tying with the previous, so we'll just fill in a 1 and a 0. 7 to 15, we're looking in these indices for an A, and there isn't one, so the best we can do is our previous value of 1. We're now on to the subproblems where we'll have 5 different M indices. We'll start with 1 to 10. We have a G at index 10, so we need a C. Our previous subproblem had 2 pairs, and the M indices to consider are 1 through 5. But since none of those have a C, there's no way that we can beat our previous, and we fill in a 2 and a 0. From 2 to 11, we're looking for an A to pair with the U. We have a previous value of 1, and we have several options for an A. When m is 2, the left subproblem is too small, and the right subproblem is from 3 to 10. We can look up 3 to 10 and find it has one pair, so that gives us a value of 2. For m equals 3, the right subproblem is now 4 to 10, which we can look up, and it also has a value of 1, giving us a total of 2 pairs. For m equals 6, the left subproblem is from 3 to 5, which is too small, and the right subproblem is from 7 to 10, which is too small, so this gives us only one pair, and our best is 2. The first index that got it for us was 2, so we'll fill in the optimal value and the index that got it for us. For 3 to 12, our previous value is 2, and we're looking for an A. In indices 3 through 7, we have A's at 3 and 6. At index 3, we have a right subproblem of 4 through 11, which we can look up, and that gives us 1. And at 6, we have a right subproblem of 7 through 11, which is too small. So the best we can do is to stick with the previous and fill in a 2 and a 0. For 4 to 13, we're looking for a G. We have a previous best of 1, so indices 4, 5, and 7 all have a G. At index 4, our right subproblem is 5 through 13, which we can look up, and it has a value of 2. So we can get 3 from this pairing, and these subproblems aren't big enough to do better than 3, so we can fill in 3 as our best value, and 4 as the index that got it for us. On 5 and 14, we're looking for a U in the range from 5 to 9. The only one we have is at index 8. And there, the subproblems we are left with are 6 through 7 and 9 through 13, both of which are too small, so this doesn't beat out our previous value of 2. On 6 through 15, we're looking for an A. We have one at index 6, and from there, our subproblem is 7 through 14, which we look up and find that it had one solution, giving us a total of 2 pairs, which beats out our previous, so we can fill in a value of 2 and an index of 6. This will carry on in much the same way until we get to the very top right of the table, at which point the whole string will be large enough that for some midpoints we will actually have a large enough subproblem on both sides that we will need to look both of those up in the table we've built so far. So I'm going to go ahead and speed through the next couple of diagonals. But along the way I noticed that I made a mistake on this entry. When solving the 4 to 13 problem, we should have been looking back at the 5 through 12 subproblem, which gave us 1, not 2. And so this entry should have been 2, not 3. And that ends up propagating over as the best so far for the next problem. So now let's stop and go through these last few subproblems in the top right corner. Here we have a start index of 1 and an end of 14. We need a U to pair with the A. The value of the previous subproblem was 4. And now, M can range anywhere from 1 up through 9. But between 1 and 9, the only instance of a U is at M equals 8. So if we pair 14 with 8, the right subproblem will be too small, and the left subproblem will be from 1 up through 7. And the 1 to 7 subproblem gave us 0 solutions. So this has only a value of 1, and we're much better off sticking with the previous 4. From 2 to 15, we're looking for an A to pair with this U. Our previous value is 3. And in the range of indices 2 through 10, we have A's at 2, 3, and 6. At index 2, we have no left subproblem and a right subproblem of 3 through 14. We look up 3 to 14, and that gave us 2, so a total is 3. When m is 3, we again have no left subproblem, and our right subproblem is 4 through 14, which also gave us 2 for a total of 3. So with an m of 6, our left subproblem would be 1 to 5, which is just too small to be in our table. And our right subproblem is 7 to 14, which only gave us 1 for a total of 2. And none of these beat out the previous, so we can fill in a 3. And we get zeros for the choice in both of these subproblems. Now when we get to our last subproblem from 1 to 15, we're again looking for an A, and we find it at indices 2, 3, and 6. And that means that we're going to get the same left subproblems we just got, all of which are too small. And the right subproblems we get are 3 through 15, 4 through 15, and 7 through 15, none of which can beat out our previous value of 4. So even though it turned out here that we never ended up adding non-zero values for the left and right subproblems, clearly as the string that we are operating on gets larger, we will definitely have more and more things up and to the right where we will get to large enough subproblems on both sides of the match, where we will need to add in both of those values to figure out what is the optimal for the current subproblem. Now that we've filled in our entire tables, we can trace our way back, starting from the largest problem, to figure out what choices we made to get this optimal value of 4. On this subproblem, we didn't benefit by splitting, indicated by the 0, so we trace back, see another 0, back again. Here we have a 1, meaning that we paired 13, which was our E, with an m of 1. So the first pair in our output is 1 with 13, and this leaves us a left subproblem that is too small, and a right subproblem of 2 through 12, so we can go find 2 through 12 in our choices table. And since this has a non-zero value, that means we paired 12 with index 2. Again, the left subproblem is too small, and the right subproblem is now 3 through 11, which we can look up, and we find that there we made our pairing at index 3. The left subproblem is now too small, and the right subproblem is 4 through 10, where we find a 0, so we go back to the previous and get that on the 4 to 9 subproblem, we pair the end with 4. And so we've reconstructed the optimal set of matches on this RNA sequence.